to reality. So effectively you have two equations that describe observable parameters. The flame spread velocity that you can actually measure and the ignition time that you can actually measure. And it's related to a whole bunch of parameters that you cannot measure directly. Okay? In a similar manner, you have the third parameter, which effectively is the burning rate. And the burning rate, again, is obtained by doing some measurements by a very, very simple analysis. Okay? So you extract from there the material properties, and this one is the one that represents the context, while these ones are the ones who represent the material. Okay? And then from here, normally people have a tendency to look at the heat release rate already as the property itself, but in reality it's a surrogate for the burning rate. Okay? So, this is the problem. Now, there's one final separation that needs to be made when it comes to testing, and it's the difference between liquids and solids. So liquids will evaporate. In other words, the molecule in the gas phase is the same as the molecule in the liquid phase. Okay? It's just simply a phase change. And the phase change basically is governed by classical pattern, in other words, by thermodynamic equilibrium. Okay? So it is just a very simple thermodynamic equilibrium analysis that tells you what is the partial pressure of the fuel in the gas phase as a function of temperature. Okay? So that's pretty straightforward. While pyrolysis is dominated by thermal degradation, as we saw, that is a very, very, very complicated problem. Now, in both cases, we're going to simplify both of them and label them the ignition. Okay? Now, in the case of liquids, it's pretty straightforward. This is a very old test, the Penske-Martens. And basically, all you're doing is you have a little heating device, you put a little bowl of the fuel, you constantly mix it so that it has a homogeneous temperature, and as a function of the temperature, you get a concentration. And that concentration is linked to the position of the pilot flame, and the moment you reach the flammability limit, you get a flash, and that's where you're going to hold it. Okay? So, in the case of liquids, we take as the onset of hazard, okay, the moment when you reach the flash point. Now, the reason why this is because the flash point in the case of liquids is not used to model flame spread, or is not used to do anything that is actually physically based. What do you think is the purpose of evaluating the flash point for liquids?
Classify liquids?
Yes, so that you can do what?
Store them system.
Store them appropriately. Is that okay? So the only purpose of the flash point is to determine the onset of hazard so you can store the material properly. So if a material has a flash point that is below the ambient temperature, you have the potential for an explosive mixture, no? So what are you going to do? Seal it. Is that okay? If a material has a flash point, so if a material is off, so if a material has a flash point that is much higher than the ambient temperature, then you don't have to worry about putting a lid. That's pretty much it. Is that okay? So what you're going to find in most codes is classifications of this sort. So class 1A, class 1B, class 1C. Okay? And they are classified as a function of the flash point. So for example, if your flash point is below 23, that basically means that you are going to gasify to flammable mixtures, below ambient temperature. In other words, you have to put all sorts of precautions to avoid having a release of flammable gases. Is that okay? It's going to cost you a lot more. Now, they always include also the boiling point. Now, why do you think they include the boiling point?
Surrogate for vapor pressure.
Okay, but what does that mean with respect to hazard? It evaporates at...
It's the point that it evaporates.
Yeah?
If you fall in explosive zone.
Yeah. So it basically evaporates, and if your boiling point is below ambient, that basically means you're going to have a massive vapor cloud. Is that okay? So if your boiling point is actually much further above, you're going to
you're going to evaporate and you're going to have a vapor cloud, but it's going to be little. And therefore your explosion is not going to be that bad. Okay? So you relax a little bit the precautions, let's put it that way. But effectively it's just purely a classification. So there's no real much physics behind the concept there. Now, and you will have basically these tables with all these flash points and boiling points, and as a function of that you have a classification, and that determines how you're going to store your tank. Is that okay? Very straightforward. Now this is where it becomes interesting. So when you do a solid, so in the case of the solid, the test that we're going to be talking about is called the lateral ignition and flame spread test. It has an ISO number and also an ASTM is E1321. It's a standardized test. Now the test consists of two parts. One part is the ignition part, where you put a sample that is 15 centimeters by 15 centimeters in front of a radiant panel in an area where the radiant panel is providing a constant heat flux. Okay? And you repeat the ignition test with this sample for a number of external heat fluxes, and you evaluate or you establish what is the ignition delay time. Is that okay? So what you're going to do is you're going to take the sample holder and you slide it in impulsively. You take the stopwatch and effectively you measure what is the ignition delay time. So then you vary the heat flux, you repeat the test, you vary the heat flux, you repeat the test, and you collect data for ignition. Okay? Then you do the flame spread test. Now in the flame spread test you use a much bigger sample, 15 centimeters by almost a meter. Okay? Now what you're going to do now is heat the sample. In this area here, you're going to have the highest heat flux, but then it's going to be decaying in such a way that each point you get a lower heat flux being imposed. Okay? Now I'll explain the nuances of the test in a minute, but effectively you heat up this, then at some point you will ignite the flame, and then you measure how fast it spreads. Now, needless to say, this test was originally developed in the 1950s, and then it was taken by Quintieri, who developed all the theory behind, and then extracted the material properties and everything. And but so it has no diagnostics. You see these little sticks here? Here. So they basically separated by a fixed distance. So you and your stopwatch figure out when the flame reaches this stick, you hit the stopwatch. When the flame reaches the next stick, you hit the stopwatch, and that's how you calculate the flame spread. Is that okay? Very basic. Very simple, very basic test. Okay, so the ignition test. So in the ignition test, what I'm going to do is I set the radiant panel to 30 kilowatts, and I put the sample impulsively, time equals to 0, measure the ignition delay time, data point. Okay, I'll repeat this a number of times, then I move to 35. I mean, obviously it will never be precise, so you go somewhere around 35, and then you set it up there, and then you measure the ignition delay time, and you get a data point. You do a few of them there, and then you go down to 25, then you go down to 20, then to 15, and so forth, until eventually you reach a point where it doesn't ignite. In other words, you can heat as long as you want, and it will not ignite. Okay? So that is basically the ignition test. Now, one of the things that is very important that Quintieri included in this test was a pilot flame. Now, why did he include a pilot flame? Because what he wanted was to be able to get some certainty on the ignition moment. If you don't have a pilot flame, a little wind can move everything, and the ignition is very uncertain. So to reduce the uncertainty of the test, he put a pilot flame. So as soon as you get the conditions, to get a lean flammability limit and get your first flash, effectively you will get that flash happening because you have this big acetylene pilot flame. Okay? The acetylene pilot flame is put above the sample, so it exerts no influence on the heating of the sample. Okay? But the products of gasification or of pyrolysis are all reaching the pilot flame, so you get the first flash, and then you will record ignition the moment the flame establishes on top of the material. In other words, the fire point. Okay? So, there you go. This is your ignition delay time, and then at some point it will not ignite. That's what is called the critical heat flux for ignition. Okay? So effectively it's a minimum heat flux that doesn't allow the flame to ignite. Okay? So these are all your observable events. The ignition delay time, and then you run it until eventually it does not ignite. Okay? So once you have that, you put a fit to the data. Okay? And that fit to the data effectively represents the theory. Okay? So let me explain how he manipulates the analysis. So if I take these curves, each of them corresponds to a heat flux. So the lowest heat flux will have the slowest heating. And as I increase the heat flux, you get faster and faster and faster and faster heating. At the beginning, for a very low heat flux, you will reach thermal equilibrium at the surface between losses and heat input before the temperature reaches the ignition temperature. As you start increasing the heat flux, eventually you will reach thermal equilibrium at the ignition temperature, and then you get a flame. And if you keep heating the heat flux, or increasing the heat flux, the curve will keep growing beyond ignition if it didn't ignite, no? Because it won't reach thermal equilibrium until much, much, much later. Is that okay? So it will be truncated at the moment it ignites, okay? And if it will not ignite, it will keep increasing until it reaches thermal equilibrium at a much higher temperature. So this is my T ignition, and you're going to have the cases where it never gets there. In other words, you get to thermal equilibrium before you reach the ignition temperature. You're going to get the critical condition when you reach thermal equilibrium at the ignition temperature. And you're going to get the cases where you will exceed thermal equilibrium, you will exceed the ignition temperature if you could, if it didn't ignite, because you have more heat than the one that you're losing to the ambient. Okay? So this point where ignition happens, this is the ignition delay time. Okay? So if the external heat flux is greater than the critical heat flux for ignition, then you will have an ignition delay time, and the sample will ignite faster and faster and faster as you increase the heat flux. If your heat flux is less than the critical heat flux for ignition, that basically means your sample will never ignite. It will never reach the ignition temperature because it reaches thermal equilibrium before it gets to the ignition temperature. And then you have the critical condition where the external heat flux is equal to the critical heat flux. And that is the case where the asymptote happens and you will reach the ignition temperature at infinity. Is that okay? So here is my equation. Okay, these are my boundary conditions. And Quintiri measured the total heat transfer coefficient, and he measured it at 45 for the test. Okay, so what does Quintiri do? He puts a piece of plasterboard, he puts thermocouples, he puts different heat fluxes, and he evaluates more or less the value of the total heat transfer coefficient for the test. And he fixes it up at about 45 kilowatts per meter square. Sorry, watts per meter square. Okay, so it's a fixed value, so we know what this number is for the test. So the heat losses are going to be represented by a total heat transfer coefficient times the surface temperature minus T infinity. And as the temperature increases, the heat losses increase until eventually they reach thermal equilibrium. Okay? So at ambient, the heat losses are 0, and then they increase until eventually your heat losses become equal to the total heat transfer coefficient times T ignition minus T infinity. Now, what does that mean? So this point here is the point where you attain ignition. Okay, so you've reached this temperature of ignition. Those are the losses associated to ignition. Now, so if this curve that is bringing me to the asymptote where Q external is equal to Q ignition, in other words, thermal equilibrium is attained at the moment where you reach the ignition, then the critical heat flux for ignition has to be equal to the losses at T ignition. Is that clear? Okay? At the critical heat flux for ignition, you are attaining thermal equilibrium at the ignition temperature. Okay? So your losses at the ignition temperature are this. And because you are in thermal equilibrium, these losses have to be equal to the critical heat flux for ignition. The critical heat flux for ignition is an observable quantity. I measured it. So this number is a number that I know. I know the HT, I know T ambient, so I can find the value of T ignition. So by spotting where the critical heat flux for ignition is, I can effectively put the thermal equilibrium condition where the losses are the same as the heat supply, and then solve for T ignition. Is that okay? There you go. I got my first property. Is that okay? So I run the test until it brings me to the critical heat flux, and then I use that value that I measured to effectively calculate the property that I cannot measure, which is the temperature to ignition. Is that okay? Okay, so there you get the first one, T ignition. So then now I have T ignition. I know what the external heat flux is for each of my data points. I know what the equation is. I made my equation solving the heat transfer equation, and I'm going to fit the data to that equation. Okay? How are you going to do that? Yes.
I have a question about the critical heat flux.
Yes.
I mean, it's just not the property of the material, it's also the property of the surrounding it is kept in because of the heat transfer coefficient, the loss that happens when it's getting heated.
Oh, absolutely. None of these things are absolute, they're approximations. So effectively what Quintieri is saying is, for the test, the surroundings are qualified, okay? But if I was to change this, and this is a mistake that many people make. So people think that they can use these values without any modification and input them into a CFD, for example. Okay, and that's not possible, because effectively this value depends on the fact that I have a 45. So if I'm going to change the configuration, okay, then effectively I will have a problem. Is that okay? Now, of course, the concept can be extrapolated, but you have to extrapolate it in a careful way, because you can use your CFD to evaluate the heat transfer coefficient, and as such, modify the ignition temperature as you are progressing in your CFD. So in principle, you could use that information to be inputted in the CFD, but it will have to be modulated by the fact that you have to calculate at each step of the process the value of the heat transfer coefficient. Is that okay? So basically what Quintieri does, he says, okay, well, this one I have, okay? So I have the ambient temperature, the external heat flux is this, and what I'm going to do is change the equation upside down. Why is he doing that? Because what he wants to do is a linear fit, okay? So he has all these data points, so then he takes the inverse of the T ignition and takes the square root. Why the square root? Because you have QE squared. So what he wants is a straight line. So this is variable y, this is variable x, okay? And effectively, you create a line where the fitting parameter effectively becomes all this term here, of which I already know this, I already know this, this is a constant, so I can extract my thermal inertia by just simply getting the slope of the straight line. Okay? So, yes?
But isn't Q second order? So how can he use a line to...
Well, because you take the square root.
Yeah,
So your variable y becomes 1 over square root of the ignition, and your variable x becomes Q.
right, but second derivative.
No, because it's imposed heat flux.
Oh,
It's what you're putting with the radiant panel.
okay.
Okay, so it's your x coordinate.
Okay.
Okay? So is that okay? So what is the intercept?
0.
0. Okay? This is a big mistake that people tend to make, that they forget that the theory requires that the intercept has to always be 0. So if you go to Excel, okay, and you basically do a line fit, and the line fit gives you a B number, that basically means it's wrong. You have to force it through 0. Is that okay? Because the theory requires you to pass through 0. Okay? So effectively, y becomes 1 over t, square root of t ignition, x is QE, and then the slope is all this, of which I already know this, I already know this, I already know this, so the only unknown is K rho C. Okay? And B has to be equal to 0. Is that okay? So the slope then is what I'm aiming at, and the intercept is always going to be 0. So effectively, you take all your data, and you plot 1 over the square root of T ignition. Here you plot QE. This is your equation, and the line that goes through 0 represents the line that takes into account the solution to the equation. This is the critical heat flux for ignition, so this gives you T ignition. Okay? Here's your critical heat flux for ignition, and effectively the data is going to go like this, following the straight line, but then eventually it's going to diverge until it lands at this point. Now, why is it going to diverge? Because the solution, this solution, remember, is a Fourier series expansion around a heat flux that is large. So effectively, the solution becomes invalid. Okay? And you can see the data diverging from the solution and landing into the other solution. That is the solution with the Fourier series for a Q that is very small, that will become this straight line here. Okay? So in one of the papers that I gave you, I put the two solutions so you can see. So this is the the low heat flux, and this is the high heat flux solution. Okay? But the fit has to go through 0, but the data that you're going to use, you have to privilege the high heat fluxes. So FM Global will say that you have to go above 30, but most people will generally go above 20, and that still gives you fairly good fit with the theory. So effectively then, all I have to do is the critical heat flux gives me the T ignition. This I know, and now I have T ignition. T ignition now, once I have it, then I can put it in here. I measure the slope, and effectively this is here, this is here, this is here, and then you get the K rho C. And with that, you get the two properties that you were looking for. Is that okay? So the first test will give you K rho C and T ignition, and the intercept has to always be 0. Okay? So you will find in tables that for different types of materials, you get T ignition and you get K rho C. Okay? Now here we have different types of materials. Okay? Now I would like to ask you a question. Why did people die in Rhode Island? Because of T ignition or because of K rho C? So if you have a foam, you can see how small the value of K rho C is, no? Well, if you look at all the values of T ignition, how different are they? Very little, no?
As a matter of fact, the foam has the highest one.
Yep. But if you look at this, if you go back to the equation, okay, look at the equation. T ignition minus T infinity appears in there, and also K rho C appears in there, and they appear as a product. Okay? So between 435 and 380, you have about 10% or 20% change. Okay? But in reality, if you look at K rho C, between the really high values of 1 and 0.03, you have about 100 times. Okay? So even the square root gives you 10 times. So effectively, you are shrinking your ignition delay time by 100 times. And because it's the square root of T ignition equals to the square root of K rho C, so it's proportional to K rho C. Okay? So your flame spread is going to be incredibly fast because of the kerosene. Now, if I made the foam fire retarded, would that help? Not at all. No? Because how much bigger I can make the ignition by fire retarding the foam? Maybe another 30 degrees, another 40 degrees, that would be about as bad as it could get. Is that okay? So effectively what you have is that it doesn't matter how fire retarded it is. I had pyrotechnics. The temperatures of the pyrotechnics are going to be 900, 1,000 degrees. So it will ignite anyway. Okay? But because it has a very low kerosene, it will spread like crazy. Is that okay? So how do you fix the problem then? You can choose another material, yes. But let's say that you have foam. How would you fix the problem with foam? If you know it is a problem with kerosene. And actually, unfortunately, because it's an acoustic insulation, the kerosene is what makes it an acoustic insulation. So you cannot shrink, you cannot increase it because it loses its properties.
Like increasing the density?
No, because you lose your acoustic properties.
Cover the foam.
Hmm? You see? You see, this is why we end up with ceramic renderings, no? Bunch of criminals here. That's what they did. So they encapsulated. That's the only solution, and that's how you end up with deck pole.
I'm not, I just said change the material.
No, but you haven't changed the material. You still have the polyurethane, and all you do is you put a barrier, okay, so that it doesn't ignite. You keep its kerosene the way it is, and you make sure it doesn't ignite by putting a ceramic barrier that is non-combustible. Is that okay? But then you've changed the problem. But you see how the manufacturers think? Just like yourselves. Okay? I give you a problem and you fix it. Okay? The problem is that now you change the problem and now you have encapsulation. And now you have to guarantee that it mechanically works, which is a completely different problem. It's not flammability anymore. It doesn't matter what kerosene is. It is about protecting it because I don't want it to ignite. Okay? Because the problem becomes, unfortunately, unsolvable. Because as you said, you have to change the material. You have no choice. Okay? So unless you're capable of encapsulating correctly, okay, there is absolutely no solution to the problem because the problem is kerosene. And kerosene is what makes it a good acoustic insulation. Without the kerosene, it's not a good acoustic insulation. Okay? So now you know exactly why people died. Because effectively, that material property represents a serious problem. Now, for example, which property would you play with if you actually had an electrical plug? So what would you like to have for an electrical plug to make it safe? Huh? Jesus Christ. Why? Yes, of course. You put a breaker. Let's say your breaker doesn't work. So you're going to use a plastic, okay? And what would you play with, you know, if you actually had the capacity to play with? Which property do you think you would like to work with? Hmm? Okay, let's go step by step. Does it matter what the ignition temperature is if you have a plug? What is the most common form of failure of an electrical plug? Short circuit, an arc. What kind of temperatures are you going to get with the arc? Very high. Is that okay? For how long? A very short period of time. So if I want to design a plug, what would I be looking for? Because I have a very short spark. My T ignition, okay, has to be longer than the duration of the spark or the arc. Is that okay? How do I make my T ignition longer?
Raise the thermal conductivity.
Well, which of the two? Because it's not only the thermal conductivity, it's K rho C that determines the ignition delay time. So which one am I going to increase?
Critical C is the only one you have because most plastics have a density of about 1. They don't differ very much from 1.
Well, you see, this is a value that I need to increase, no? So I will be looking for the material that has the biggest K rho C possible, no? Is that okay? Because that will create the longest ignition delay time, and therefore the arc is not capable of igniting the material because it doesn't have time to ignite the material. And yes, the problem is that most plastics are going to have values around 1. Okay? Now the best one in this case will be this plastic PMMA, but it's unfortunate that actually PVC has actually a much higher value. And that's so it has higher ignition temperature, but it also has a higher K rho C value. So effectively, you're picking up a material as a function of the property that you want to play with. Is that okay? So you have a tool that helps your decision making. Okay? So the next one is the flame spread. Okay? So effectively, I'm going to take now the same problem. I know K rho C now, and I know T ignition. I know the critical heat flux. So what I'm going to do is I'm going to set this heat flux here above the critical heat flux. Okay? So I'm going to put it a number that is above the critical heat flux. So I know that it will ignite. So the flame spread will start. And then the flame spread will start spreading into less and less and less external heat flux. Now the question is, why does he do this decay? And this is the most intelligent part of the whole test. So here you have a decay, and he achieves this decay by putting an angle between the radiant panel and the sample. In the area where it's very close, the decay is almost imperceptible, so you have pretty much a constant heat flux. He guarantees that this is above the critical heat flux, so it will ignite. And then he waits for a very long period of time until the entire material reaches thermal equilibrium. At that point, he will ignite. Okay? So he's going to wait until the entire sample has reached thermal equilibrium, and then he will ignite. The flame starts, and then it starts spreading into a material that is in thermal equilibrium with the external heat flux. Okay? And you will see why he does that. So, by doing that, he constructs a flammability diagram. Okay? Now, the flammability diagram is very interesting. On this branch, you have the ignition delay time. Okay? And here's the T ignition. So this data corresponds to external heat flux and ignition delay time. The other branch corresponds to the flame spread. Okay? Here is the velocity of spread that is being measured. Now, the flame spread will asymptote at the critical heat flux for ignition. Why would the flame spread asymptote at the critical heat flux for ignition? Okay, so in which case is dominated by the preheating by the panel? When it's closer to 0, no? So effectively, if you are below the critical heat flux, you've warmed up the material, but you cannot ignite it. So you still need the flame to provide heat and ignite it. Is that okay? If you are above the critical heat flux, you're already gasifying and producing a flammable mixture. So effectively, you get a premixed flame going through the whole thing infinitely fast. Is that okay? This is why it asymptotes, because you have already gasified ahead of the flame. Okay? So the flame acts as a pilot that ignites a premixture of fuel and oxidizer. Is that okay? And the velocity of a gas phase flame is much, 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 much faster than the flame spread velocity over a solid. When you're below the critical heat flux for ignition, You have preheated, but you're not gasifying. You still need the heat of the flame to bring you there. Is that okay? So, the flammability diagram at this end is flame spread, and at this end is ignition. And they both asymptote at the critical heat flux for ignition. That's the verification. So by plotting the two of them together, and because the two of them asymptote in the same place, you've validated your critical heat flux for ignition from both sides. Is that okay? So this number now is confirmed. Is that clear? Yep. So what is happening with the flame spread? It's exactly the same problem as before. Okay? You're going to have your ignition temperature, you have your asymptote, which is thermal equilibrium at the ignition temperature. This is above, this is below. So this is your ignition delay time, this is above, and this is below. And then you have the case where the external is equal to the critical, and that's where it asymptotes in the middle. Okay? Again, you have the same equation, you have the same boundary conditions, you have the same HT. These are your losses, loss 0 here, and these are the losses when you reach the ignition delay time. Sorry, the ignition temperature. Okay? So this is the boundary condition at all values of the external heat flux. Okay? This is the external heat flux, and these are the losses. Okay? The moment that I represent the losses here, this is the surface temperature. Okay? And this is the ambient temperature. Okay? So your external heat flux is equal to this. Why is that the case?
Because you're in equilibrium.
Exactly. So because when I was preheating, I waited until I was in thermal equilibrium, no? So effectively, each surface temperature is going to be the thermal equilibrium with the external heat flux at that location. Okay? Now, why does he do that? The reason why he does that is because that allows him to plot the flame spread as a function of the external heat flux. Okay? So, because he knows that the external heat flux is bringing you to thermal equilibrium, and therefore he can relate the external heat flux to the surface temperature, and therefore he can relate that to my solution to the flame spread equation. Okay? So, you're happy with this. Okay? So now, if I go there to my equation, this is my equation of flame spread. Okay? At each point in x, the flame spread velocity is this parameter phi, K rho C, T ignition minus T ambient. Okay? Ambient meaning the temperature of the solid, no? Because I am here with my flame, and I have to bring the solid from the temperature in which it was to the temperature of ignition. But the solid is the temperature of the thermal equilibrium. Is that okay? So this Ts now is the Ts that comes from here, because I have brought it to thermal equilibrium. Is that okay? So what I'm going to be doing is bringing the solid from the temperature that it has at this point to the temperature of ignition, and then the flame can spread. Okay? So I add and I subtract T infinity. So I'm going to add T infinity and subtract T infinity, which changes nothing. But the reason why I do that is because T ignition minus T infinity is my critical heat flux for ignition, and T infinity, Ts minus T infinity, is my external heat flux. Okay? So what I'm going to be doing then is I'm going to multiply this by HT, and I'm going to divide by HT, but because it's squared, this HT now that I divided with is going to go to the top. Okay? Remember that you were saying that effectively this is also a variable associated to the environment. So by bringing the HT into the phi, he's bringing again another variable of the environment into that property. Is that okay? So effectively, by multiplying this by HT and dividing it by HT is squared, so I'm going to get the critical heat flux for ignition minus the external heat flux. Okay? So I'm representing my flame spread as a function of the external heat flux and a function of the critical heat flux. This I know, this I know, this I know, and now I can evaluate the value of phi. Okay? So I put capital phi here because this phi is different to the other one in the sense that now it incorporates the heat transfer coefficient. Okay? So your critical heat flux for ignition is HT T ignition minus T infinity, this term here. Okay? And your external heat flux is HT TS minus T infinity, and this corresponds to this term here. And therefore, that enables me to create that. Now, I do the same thing, turn it into a straight line by putting the inverse and then taking the square root so that the square disappears. This becomes x, this becomes y, and it is a straight line. Okay? The slope now, since I know k rho c, will give me the value of phi. Okay? Now, the intercept now is the critical heat flux for ignition. Okay? So I can actually plot all the data, get the slope, and effectively find the value of phi. Now, this is the mind of an individual that actually thinks with very clear and solid theoretical arguments, but has an incredibly, sort of astute practical motivation. Okay? With one test, he's getting hundreds of data points. So he only has to run the flame spread test once. And he has so many data points that he can do his line fit perfectly, find the value of phi, without even having to repeat the test. Because depending on how separate he puts the two sticks, he can create more and more and more and more data points. Okay? So effectively, with one test, you pretty much have everything that you need. Okay? So effectively, he brings into the test the whole theory in such a way that then the test represents a physical concept that is meaningful. It's not a brute force test like what we saw BS 8414 or NFPA 285. Remember the big test where you put a crib and you burn it and that's it, pass fails? No, I mean, this is a test that has really very thorough fundamental physical principles. And these fundamental physical principles are presented in a way that is so elegant that it delivers everything that you need to get a sense of what matters, what dominates the problem. Now, clearly, it is a simplification, okay? And this was done in the 1970s, okay? And the purpose of it was to give you physical insight. It was not to use it as an input for a CFD code. He never thought of it as the input for a CFD code. He thought of this, I'm doing this so you understand what matters. Okay? Now, obviously, then we forgot all the fundamentals. We forgot the physical meaning of what he was doing. We forgot the practical reality of what he was trying to attempt. And we start plugging it into a CFD code. Okay? Now, again, I'm not saying it cannot be done. But it cannot be done as the default of FDS. Okay? About 10 years ago, FDS had a default library, where they actually had all these parameters extracted from Quintieri's paper. Okay? And it was so misused that eventually NIST took it out of the library. Because the problem is that these numbers were never, ever intended as being numbers that were associated to a CFD code. They were just simply purely for physical insight. Okay? So that you could understand what controls flame spread. Okay? So effectively what you have is that flame spread is going to be controlled by the T ignition, it's going to be controlled by K rho C, and it's going to be controlled by this flame spread parameter that effectively amalgamates all the environmental variables associated to the interaction between the gas phase and the solid phase. Okay? We cannot calculate those things correctly, so what we do is we try to estimate it from the test so that we can separate material from the environmental variables. So now we have this, and from the slope you get that, and then you get a list of all the different values. Now, one of the really interesting things is that it gives you a very strong sense, okay, of what materials are trouble. Okay? So if you look at this, most materials are around 0.01, 0.02, 0.01, 0.02. Then, interestingly enough, wood has a very strong flame. Okay? Because when wood is spreading on the surface, the lignin dominates the problem. Wood only dies when it starts charring, and then the char produces a thermal barrier. But the lignin is actually a very easy material to burn. Okay? So the gasification of the lignin effectively is delivering a very strong flame. Now, the worst of them all actually ends up being nylon. So why do you think nylon is so bad?
Gasify easily.
That's exactly what it is. So basically, it breaks extremely easily. Okay? So you have a very large amount of fuel that comes in, a very high temperature of the flame, a very, very, very strong value of Phi. Okay? So in a way, this becomes a bit of a surrogate, to the decomposition chemistry. And it gives you a sense of which one is a vigorous decomposition chemistry and which one is a weak decomposition chemistry. So the final parameter is the heat release rate, and that's the one that I actually don't like, because it's just basically brute force. Okay? So the reality, as I explained, is that you know what mass of oxygen comes in, what mass of oxygen comes out, and basically what we do is just simply measure those two things, and that gives me an estimate of what is the heat release rate. That requires my assumption that the heat of combustion has to be the heat of complete combustion. And the way I obtain that is by basically putting this under the hood, controlling the exhaust, and making the measurements at the exhaust. Okay? And it's a very, very straightforward, process. This is a very conventional test nowadays. People do it all over the place. It's standardized, ASTM E1354, and effectively it's a standard test. And here are all your gas measurements. That's the duct. The blower will control the flow rate, and effectively here's where you make all your measurements so that you get your oxygen concentration. Okay? Now, this one will have multiple measurements. They will have CO, CO2, soot. Why? Because many times what they're trying to do is reconstruct the incompleteness of combustion. So they put corrections that enables you to assess how incomplete your combustion is. Okay? Doesn't really add or change much the results. Now, how is this thing normally going to work? So if you have an ideal test where a material is burning perfectly, it will ignite, it will start burning with a constant burning rate. Okay? The decrease of mass as a function of time is a straight line. And because the constant is a constant burning rate, the constant heat of combustion, you will get a straight line, and this will be your heat release rate. So if you divide the heat release rate by the area, you get what is called the heat release rate per unit area. And effectively, that heat release rate per unit area substitutes, okay, the combined values of the burning rate per unit area and the heat of combustion. So the heat of combustion times the burning rate per unit area gives you the heat release rate per unit area, which you can extract straight from the test. Okay? You don't need the heat of combustion, you don't need the burning rate, you combine the two of them in the heat release rate per unit area. Okay? So if you want to get the heat of combustion, you divide the heat release rate by the burning rate, and that gives you the heat of combustion. So you can play around with the whole thing, but this one is actually a circular calculation, no? Because you assume complete combustion to calculate complete combustion. Makes no sense, okay? But anyway, so That's a test. That's what the ideal test looks. So this is a typical set of data of an ideal test. So in this particular case, it's kerosene, and as you can see, it ignites. Once it ignites, it oscillates a little bit, but it burns almost at a constant value, producing a heat release rate per unit area of approximately 430, 440 kilowatts per meter squared. Okay? Now, if you decide to change the material, and now we're going to do gasoline. So what happened there? It's not constant anymore. Why is it not constant anymore?
Different fractions coming out.
Yeah. So you're distilling. No? So effectively, at some point, you're taking the more volatile fractions, then you're taking the next one, then you're taking the heavier fractions. So effectively, you have step values. Okay? So if you had to use this data to calculate the heat release rate per unit area for design purposes, which value would you use? Sorry? So Tarek says the highest. Do you agree with him? No. Why? Okay, so you've qualified it. You've said too conservative. Why is that too conservative?
Because it's not representing heat release rate.
So in other words, what you're telling me is that everybody will be safe here, but then you will kill everybody here, and then by the time you get here, there's nobody left. No, I'm just asking. I want to understand your motivations. Yeah.
I would take the sum, I think.
So, sorry, what do you mean by the sum? The average?
No, the sum under the curve.
So you will integrate the whole thing. That will give you the total energy, and then to get the rate per unit time, you will still have to divide by the time. You know, which will be an average. So you're in the same murder streak as he is.
No, for the total amount of heat release rate, like that's our purpose to calculate, right?
Well, you just used the key word. What's the purpose for this calculation, no? Okay, so why would I use this plot? That's what determines what is important. So if I'm doing it for smoke management, okay, where it's going to be almost an integrated process in time, where effectively, remember the calculations we did yesterday. So you're integrating in time as you're accumulating the smoke layer. Is that okay? So effectively, using an average value might be okay because I'm integrating in time. Is that okay? Yeah.
Maybe relate the heat release rate to the smoke production rate.
Yes?
And somehow correlate them together over time.
Yes, but the question will be, what will be the purpose? So if the purpose is to dimension your smoke management system, in other words, you need to calculate how much smoke you're producing so that your fan can extract it, because you're going to have a very long period of time while the smoke layer is descending. Okay, using an average might be appropriate, because effectively it doesn't matter what is happening at this point in time or what is happening at this point in time. What really matters is what happens on average through the whole process, because I'm sucking smoke at all periods of time. Is that okay? So at some point, if the heat release rate goes a bit up, then maybe the smoke layer descends a bit faster, but then afterwards it will slow down. So effectively I can compensate the two. So if it's for smoke management purposes, an average might be probably appropriate. Is that okay? In which case you will go with the maximum value. Sorry?
Fire growth?
Yeah, but what will be the purpose? So why would you be calculating fire growth for?
Like safety, you know, to see how quickly you get people out of that.
Yes, but how does that value enter the equation? So if you're talking about tenability, you're talking about life safety, you're talking about these things, what is the value that you're calculating. You're using this heat release rate for a purpose, and that purpose is to establish how fast the smoke layer descends. So we go back to the smoke management problem. In which case I would like to use the maximum value.
When the time matters, like
In which case would it matter? Think of a purpose. Yep.
Structural design, I guess.
No, because you see, structural design is the other side of the problem. So we're in the growth period still. We haven't even got to the structure yet.
it's like we have a high flammability material that we don't want to start degradation.
Okay, then now you're talking. So what happens, for example, if you have several materials right next to each other? Okay, in which case, effectively, is the growth rate that determines when the other material is going to ignite. Okay, so in that case, I rather use the maximum value because effectively that will give me the shortest compromising of the other components. Okay, so potentially that could be an example where time really matters because you are attacking other things. So you want to be careful not to use a value that is not conservative. Okay, now, and then when you wish that reality was only this complicated, then you have this. So what happened there?
You melt and then vaporize.
Yes. So effectively what you get is a phase change. So here, what you have is a material that is a solid. And what you get here is a material that is a liquid. And the two materials are effectively, thermally speaking, very different. Okay? But what about the heat of combustion? So if I was to plot the burning rate, not the heat release rate, but just the burning rate, how would that plot look? So that's the heat release rate per unit area. How would m dot double prime look? Exactly. Not almost the same. It will actually look exactly the same. No? Because effectively what you have is this, and it goes like this. This will look exactly the same. Because once it changes phase, what you have is a much higher evaporation rate. You have the same feedback because the flame is not changed very much. And effectively, what you have is you need a lot less energy to evaporate. So your burning rate will actually look like this. So how would your heat of combustion look? Is that okay? And that heat of combustion corresponds to what? The complete heat of combustion of naphthalene. Is that okay? So what you've defined there is effectively the phase change is going to change dramatically the burning rate. Okay? And when you thought that this was as complicated as it gets, then this happens. I'll let you watch it because it's quite entertaining. There's a few jumps in time. What has happened with the material? It's swelling. So this looks like a big cake of carbon. Look at it. It's an intumescent. So it starts getting into the cone and it starts doing all sorts of weird things. And this is the moment when you actually calculate your heat of combustion and it comes very different. So you call it effective heat of combustion. And the reason why it's coming very effective is because you're changing the test as the thing is coming into the cone. Okay? So, you know, these things can get really complicated, and that's the moment where we actually get lazy. Okay? And how do we get lazy? We get lazy because we start building these massive cones. Okay? So look at the size of this person. So we are literally putting the entire storage rack, you know, inside the thing, because we cannot think anymore. This is too complicated. Okay? So we have to go real. You know, there's no way we can solve this problem. We have to go to the real scale. Okay? And we start putting, you know, storage racks. You know, we have burning sofas. You know, it's like, you name it, and then you get these weird curves, and we don't know what to do with them. And what average are you going to take in there? Nobody has a clue. And then, of course, then you get the bunk bed, and you name it. So we start creating one after the other one because we do not know better. Okay? Here we have these very elegant theories. We have all this work. We did all these things. We get to this understanding of the problem to a level of profoundness that we think that we're being elevated, you know, somewhere up there. And then what happens? Crash landing. You know, all of a sudden we are burning bunk beds. Okay, and effectively, you know, you name it. You know, sofas, chairs, mattresses. I mean, it's incredible. If you go to the libraries, people have been doing this to the point that it's actually almost obsessive. You know, you wonder, why do they need all these curves? But anyway, so effectively you can reconstruct the real thing and have as many of these plots as you possibly want. And you have here 3 examples of libraries where you can find all these heat release rates in as much detail as you could possibly want. So effectively, as you can see, what have we done? So we started saying, okay, what really matters is the way in which we perceive the problem. Okay? Once we understand how we perceive the problem, we understand what are the things that we need to solve. You know, once we understand what they need to solve, we have to recognize the limits of our understanding. And we recognize, for example, that we're not going to resolve the full-blown combustion, so we have to learn about combustion to eliminate combustion. Okay, hopefully we don't have to eliminate to the point that we're burning a bunk bed. Okay, but the reality is that we are eliminating the complex parts of the problem, retaining the parts that are very important. So I explain how do you manage life safety within a compartment, and how do you actually bring all the problem into this alpha t squared. Okay, but this alpha that we had assumed as being just simply a number that brings certain material properties, then when you break it down, you realize that it's a combination of the material and environmental properties. And there is a very clear physics that tells you which are the parameters that dominate the problem, which ones are related to the materials, and which ones I'm introducing that are part of the environment. So if I want to use those properties and the conditions are different to the test, I have to make corrections. Because the heat transfer coefficient is not going to be 45, it's going to be something different. And the phi is not going to be what it is, because it has to be consistent with the geometry that you're burning. So we start understanding how all these things start fitting, so that we have the capacity to use our brain in a way such that we modify the numbers, or we conduct further tests, so that we fill the gaps of what we need to know. Okay, and then all of a sudden we can use this information in whatever way we think is appropriate, because we understand what the limits and bounds of that information is. Okay, so effectively we've walked through the whole problem of life safety, and we are at the point where we have flashed over. Okay, so we understand the limitations of what we're doing, we understand the coarseness of what we're doing, we understand the variability and where things are coming from, and we can create a story that more or less brings me to the point of flashover and the end of the life safety problem. Is that okay? So then what comes next, my room has flashed over, I have a fully developed fire, and I need to be able to address the structure. Okay? Now the problem of the structure is purely a problem of heating. Okay? For a fire person, it is about delivering the appropriate heating to a structural engineer, so a structural engineer can do their job properly. Okay? I'm not going to touch on the structural parts, because in principle, theoretically, I'm not competent in that space. You know, I'm not a structural engineer. I should not be doing structural calculations. What I'm supposed to be doing is delivering for a structural engineer the evolution of the temperature of the system, so that they can do their job of doing the structural analysis. Okay? So what I'll do is I'll create the fully developed fire, the boundary condition for the structural engineer, and the basic heat transfer equations that allows you to establish how the structure heats up. Okay? And with that information, then you hand over to the structural engineer, because the one, you know, when you deal with safety, the one thing that you always have to keep in mind is that it is a professional practice. Okay? And as such, okay, the first rule of thumb of professional practice is you never, ever exercise beyond the bounds of your competency. Okay? So starting doing finite element models, structural analysis, and all these things is outside the bounds of my competency, and in principle should be outside the bounds of a combustion summer school. Is that okay? So I'm going to stop at that point, but effectively going to explain to you how you actually give the boundary condition to the structural engineer. Okay, so we'll stop here, and we'll pick up the final class.